Hello, my name is Jed Murdoch and welcome to Module 2 on demographic stochasticity. In this module, we'll introduce the idea, the concept of demographic stochasticity. We'll talk about how it affects populations, both large and small, and why it might be an important concern for managing species or conserving species. So as conservation biologists, as managers, let's say, we're oftentimes concerned with trying to better protect a population of plants or animals. That might be perhaps blunt-nosed leopard lizards in California, Salt Creek tiger beetles in Nebraska, gray wolves in Wyoming, and so forth. So we spend a lot of time and energy trying to figure out what factors affect population, what factors affect population growth and size. And certainly there are quite a few. We know that humans can have an influence. We can affect habitats. We can affect the fragmentation of the landscape, and that can certainly have an influence. We know that things like food, habitat availability, predators, competitors, pathogens, all those sorts of things can have an influence on the stability or the viability, let's say, of a population. But there are other things too. There are random processes that we need to be aware of also. So there are what we refer to as being stochastic processes. So stochasticity refers to random variation, or basically random processes. And we know randomness can have real effects on a population. So we know that randomness can affect populations' genetic makeup. It can have an effect at the genetic level of a population. We know that genetic drift, and incidentally we have a module on genetic drift, can in fact change allele frequencies due to randomness in a population. We also know that populations at sort of a bigger, more macro level can be affected by randomness. So we may have random events. We may have some catastrophic weather event, let's say, or some change in food supply that affects the growth of a population. And those events, again, might be random events that just happen. We also know that randomness can kind of weasel its way in and affect individuals. It can affect populations at the individual level. And it's that form of randomness that we call demographic stochasticity. It sounds like a complex term, but I think by the end of this module you'll have a better sense for what it really means. If we had to give it, I guess, a proper, more technical definition, we would call demographic stochasticity really the average variation that we see in the survivorship and reproduction in a population, because those individuals in a population are integers. They're whole numbers, right? We don't have fractions of plants and animals existing out there in the world. So again, this sounds like a complicated definition, but in reality it's a pretty simple concept, and I think it'll become clear as we go through this module. So let's start with an example. Let's consider the panda, right? We're all familiar with the panda, lovely creature, iconic creature of Asia, very charismatic. We see that pandas live in sort of the mountainous ranges of parts of China, and it happens to be a threatened species. Let's say we spent many years monitoring a panda population and studying its population dynamics. So we may have captured some of these pandas, we might have marked them, we might have sent them on their way, and then spent quite a bit of time following their fates and following their patterns of reproduction. So if we follow reproduction, we see that females are reproducing on a regular basis, and we could monitor how many animals are recruited into the population each year. We could also follow the fates of our individuals with markings, those wearing radial collars, for example. And from those data, we could generate an average birth rate and an average survival rate for individuals in that population. So let's say our average birth rate for an individual is 0.4. That means that each female might produce 0.4 offspring on average every year in that population. We could also say that the survival rate is 0.6. So we'd expect 60% of the population to survive on a yearly basis, right? But we know now that individuals, right, are integers. They're integers, they're whole numbers. So we don't have 0.4 of an offspring, let's say, being born into the population on a yearly basis. We don't have 0.6 of an individual surviving from one year to the next. These are average measures, and we're dealing with integers. So if we think about a small panda population, let's say we're in a nice mountain range and we have a very small population of 10 individuals. We've got 10 pandas. And for now, let's just consider survival, right? Survival probability. If our survival, our per capita, per individual survival rate, again, is 0.6, what does that mean? That would basically mean that we'd expect 6 individuals out of that 10 population to survive to the next year. It's a 60% survival rate, really. So 6 out of the 10 we would expect to survive. But we know from year to year, we don't exactly have always 6 individuals surviving from one year to the next. There's some variation because we are estimating that survival as essentially a mean rate, as an average rate, and there's some variability around that. So in some years we might have 5 individuals surviving. In other years we might have 7 individuals surviving. In some years we might have 4, and others we might have 9. And over time, among all individuals in the population, we would have on average 60% or 6 individuals surviving. But there's some variability, and that's variability in some respects is due to randomness. If we think about another population, let's say there are 9 individuals, to take this further. Out of 9 individuals with a 60% survival rate, a 0.6 survival rate per individual, we would expect how many to survive the next year? Well, we'd probably expect 60%, which ends up being 5.4, but we know 5.4 individuals can't survive. We know that either 5 or perhaps 6 will survive. And whether 5 or 6 survive till the next year is really a random event. It's a random chance roll of the dice in many ways. So this randomness, this random variation is really the realm of demographic stochasticity. So let's see how this plays out now. What I'd like to do is cover a few basics of population growth and how we model it. And then we'll look at how that randomness, that random variation that we just covered, plays out in a couple of populations of pandas of different sizes, a small one and a relatively large one. And we'll see the effect that that randomness, that stochasticity, in fact has. We'll then build a spreadsheet. My colleague Terry will build this spreadsheet that will walk you through this procedure that we'll cover. So let's start with some basics of population growth. So to model births and deaths, let's put some notation to the basic measures that we've covered, right? So if we want to estimate how a population will change, let's include a couple of things here. So we have a value here called NT, and that's just simply our population size at present, or our starting population size for our pandas. We then have this value NT plus 1, and that's basically a measure of what we expect the population size to be like one time step into the future. And that, of course, is in some ways reflective of the number of births that we have, so that's an important term to consider, as well as the number of deaths. So the T here basically means that the births and deaths we are seeing are those that occur between T and NT plus 1, or T plus 1 rather. So in this case, let's consider this population to be closed. So we're considering our pandas here to be a closed population. In other words, there's no immigration, there's no emigration that's occurring. And if we make that assumption, then we can build a basic population model that looks something like this. And all this model states is that we expect our population size in the future, one time step down the line, to be equal to our starting population plus the number of births that occur, right? So those are the number of individuals that are recruited into the population, minus the number of deaths. So those animals that die obviously have to be removed from our estimate. Now, oftentimes in wildlife studies, we don't necessarily know the true number of births and true number of deaths. Imagine yourself here in China, you're studying a population of 1,000 pandas, probably doesn't exist, over several thousand square kilometers. It's very difficult to arrive at those raw numbers. We could do some sampling, we could sample a certain proportion of that population to get at those numbers. But they are fairly challenging to arrive at. If we can estimate those numbers, another point to consider is that there are very few assumptions we can make about them. They're just numbers at a particular time period. And we can't really do that much in terms of modeling. There's not a lot of utility to one set of numbers. To solve this problem, oftentimes when we're modeling populations, we use average birth rates and death rates that are per capita. So these are rates per individual as opposed to raw numbers. If we have per capita rates of birth and death, there's a lot more that we can do with those values. So if we assume that total births and total deaths are governed by our per capita rates, then our equation would be the following. Our equation then would of course be this. So our population change, what we expect our population to be, is what it is now, plus those individuals, some measure of the number of individuals born. So here we're substituting in our per capita birth rate for B, minus those individuals that die. Again, we're substituting in our per capita rate for death. And again, that will produce some measure of how the population changes. So let's consider a population of pandas again. Let's say we've got 10 individuals and we've followed them for some time, and we've managed to estimate among those 10, well, let's say among a larger population, a birth rate of 0.4 and a death rate of 0.4. So we've got these measures, and we'll now apply them to our population of 10. So we'll look at how these measures affect the population as a whole. So when we do that, we have our raw number of births really being our birth rate times our population size. So if we estimate that, our birth rate is 0.4 and our population size is 10. And when we multiply the two together, we end up with a value of 4. So 4 animals are being born into this population based on our rate. Same with our death rate here. We've got our deaths being a function of the rate times how many individuals in the population. So our death rate is 0.4 and our population size is 10. So here we estimate 4 animals will die. 4 of our pandas, unfortunately, will die. Incidentally, we can also estimate survival. So this is our survival rate. So survival is similar to deaths, right? It's the opposite of deaths. So how would we estimate survival rate? Survival rate is just 1 minus our death rate. So if our death rate here is 0.4, what then would our survival rate be? It would be 0.6, and we could apply that to the population too, and that would give us a measure of 6, and of course 6 plus 4 gives us 10, so they're just basically reciprocals of each other. So at the population level, we have 4 births, we have 4 deaths, and they cancel each other out, so at the end of the day, our population hasn't changed from one year to the next. So this gives us a measure of how these rates can affect the population. But we know that demographic stochasticity is this variable effect, this effect of random variation on individuals. So what if we apply these numbers to individuals, to the fate of individuals, and not to the population at large? If we do that, we may not end up with exactly the same birth numbers and death numbers that we're seeing here because of this integer issue, because individuals are not partially born or partially dying within our time period. So we know that's generally not possible. So we can do this. We can simulate the fate of individuals pretty easily using a spreadsheet. And we can model the fates of these individuals, see how that affects the change in population over time, and compare to what we've just done.